Okay, hey everybody, I'm Victor.
I'm Kennedy.
I'm Kyle.
I'm Noah, and we're going to be doing cryptography and primes.
Oh yeah.
Yeah.
You heard that. Cryptography, the big C and the big P. You already know who I am. I'm Victor. I'm gonna be teaching you all the basic definitions in order for you guys to fully understand cryptography. If you don't know, so basically, we're gonna start off with the most basic word here, which is cryptology. Cryptology is the study of codes and the art of breaking them and creating them. So basically on any computer, or basically back in the Roman era, you could say, codes have always been used to keep sensitive data from being leaked into enemy lines or people you simply just don't want to have them. So cryptology has existed for a long time, since the Caesar cipher being created by none other than Julius Caesar, going by the name. Encryption is the process of converting data into code, data or plain text in this sense. Plain text meaning that it's readable data, we can read it by ourselves without any form of key or anything. Decryption is the process of converting a already encrypted code into plain text or data that we can read, which is what it usually starts off as. The cipher is an algorithm or a set of steps performed in order to convert data either into a code or vice versa by breaking the code and making it readable data. A key is typically the string of bits, meaning in this case just words or letters or characters used to change encrypted messages into decrypted messages or vice versa.
Another cipher I'm going to show, this one is going to be a Caesar cipher. Caesar cipher is a shift cipher, meaning you just shift the entire alphabet over by a certain amount. This one we shifted the alphabet backwards by 5. So now A equals F, B equals G, C equals D, and so on. So example, let's do, what should I do?
GSW, yeah.
Woo! Alright, let's do GSW. G will be L as it corresponds to, S corresponds to X, and W corresponds to B. So now this is what you would send. Though this cipher is probably a bit more secure than the app batch, still really easy to break as long as you know how many to shift the bottom key encryption by. So if you were to do that, you can still easily break this one.
So, all those ciphers that Kyle just showed you are completely useless today because of computers and their incredible computing power. So, there are modern day encryptions that are used on the internet all the time. They're used mainly, or commonly, I guess, they're used commonly in protecting bank information, hospital records, and government servers from malicious hackers and programs. Also, a fun fact, if a website URL is preceded by HTTPS, it's encrypted, and the S stands for secure.
So I'm going to be telling you about the roles of primes in cryptology. So primes play a very important role. As we showed, as you saw in the activity, RSA focuses mainly on 2 prime numbers that you choose. In the case of RSA, the numbers were P and Q. So we showed you a simple example, P being 5 and Q being 7, but Kyle also showed you an example of relatively small prime numbers compared to what is commonly used in encryption and decryption. Those prime numbers were each 6 digits long and led to the number n being 58 billion-ish. And those are, like we said, using small prime numbers. The wonderful thing about prime numbers is that it's very hard to factor a semi-prime number. A semi-prime number is a number resulting from the multiplication of 2 prime numbers. And it's vastly harder for a computer to factor out a semi-prime number than it is to compute a semi-prime number. So it's much harder for a computer to take apart a 24 million digit long key and factor it out than it is to make that key. So semi-primes are commonly used. We also use the term coprime, or relatively prime, or also primitive root. And this is a number that is relatively prime, which means that the only factor it shares with a specific number is 1. Coprimes are useful because when you multiply things together or using specific keys, it's important to have numbers that can't be ambiguous for something else. So to have numbers that are specifically their own and can't be multiplied to get some other number. All right, so we're gonna be going over why RSA is so unbreakable. We touched on this a bit during the activity, but here's more in depth. So you always start with 2 prime numbers. I'm gonna use the same 2 prime numbers we used before, 5 and 7. You begin by multiplying them together to get 35. Next, we need to find R, which is also called the totient of N. We went over this very briefly, but in number theory, the way that you find the number of coprime numbers using a semi-prime number, 35, you take the first prime number, subtract 1 from it, and then you take the second prime number and also subtract 1 from it and multiply those 2 together. So this means that there are 24 numbers less than 35 that are coprime to 35, which means the only factor they share to 35 is 1. So there are 24 numbers below 35 that only share a factor of 1 with 35. Next, we need to find the encryption and decryption keys. And the way we do that is we solve for k mod r is equal to 1. You know, remember modulus is just finding the remainder. So if k was 5, mod 2 is still going to be 1. Because 2 goes into 5 twice, it doesn't matter, but the remainder is 1. So 1 is returned. So the way we do this is we take k mod r, mod 24 in this case, and try to find some number whose modulus is 1. Modulus of 24 is 1. So in the case that we showed, we chose 19 times 19 mod 24 is equal to 1. And each of these numbers corresponds to an E or a D. So the restrictions on E are very few. E has to be greater than 1, E has to be coprime to totient of N, which in this case is 24, and it must also be less than the totient of N. So 19 works for E. In the example given, D in this case is also 19. But the reason we don't use 19 is just that way we don't confuse you. We could still use 19 and it would work, but it's a lot easier to just work with 43 in this case. So that way we're not writing 19 a bunch of times. Also in RSA, the only 2 things that are shared or that are open, that are public, are the E value and the N value. And this is because those are the 2 numbers you use to encrypt something. Knowing P, Q, and R would lead to you being able to easily solve for D. And that's not good, because the only people that should be able to decrypt this are banks, are hospitals, are the government. And that's why this is still used today. But the reason it's so unbreakable is because finding the factors of a semi-prime number is very difficult. So in the example Kyle provided, the semi-prime number n was 58 billion. It's a lot harder for humans to factor that out, but it's also a lot harder for computers to factor it out. It's a lot easier to multiply 2 large primes together and get a result than it is to factor out a semi-prime number.
Hey guys, now we're going to be talking about Diffie-Hellman. This is used to exchange keys securely in order for them not to be taken by anyone who shouldn't be having them. So in order to start off, we're going to just pick a P and a G.
So P is a prime number, we'll call it 53, and G is a number that's co-prime to P minus 1, which is 52. We're going to do a number 31.
A and B, we'll get these in a little bit after doing modulus, but for now, we're just going to pick random numbers. For example, I'm going to pick 7.
And I'm going to pick 23.
Okay. Next, we're going to do a modulus function again. This time with G getting put to the power of B. So for me, that would be 31 to the power of 7 modulus 53.
And for me, it's G, which is 31 to the power of A, 23 modulus P 53, which is capital A, which for me is 21.
For me, my capital B will be equivalent to 33. And now we're going to switch our numbers. So I'm going to get his 21 and he's going to get my 33.
And these parts of our equations stay private, while these numbers will be public. So now that I've got his B, which is 33, I take B to the power of A, 23, modulus P, which is 53, and that gives me 35.
I did the same thing with his 21 and put it to the power of my lowercase b, and once again modulus 53, and I also got 35, thus showing that we have the same number and we can securely trade off keys.